the lecture by Professor Misha Gekhtman, and today's title is Cluster Integrable System.
Right. Thank you. I will get to this. So this is third part of my title, so I have to get to it. Well, sometime, and today is the day because there is no other day. And I also have to comment on that. So I just copied this from my name tag, and so it's not next year this decap. It's my number here at the conference. Before I actually get into cluster dynamics or cluster integrable systems, I want to start with what we were considering last time, was this networks representing totally positive matrices. And on the first day, I promised a network proof of Gekhtman-Crane theorem on spectral properties of totally positive matrices. So I'm going to sketch that, and that will actually help us to talk about dynamics as well. I'm going to deal with this 3x3 example, but as we know, it's very easy to reinterpret it for other sizes. So this is my now arbitrary totally positive matrix, which can be obtained through a network in which I'm not going even to draw the weights, because all that's going to be important for me is combinatorics of the network. And I can choose, as we know, this network based on any selection of two reduced words for the longest permutation. So here it's again 1, 2, 1, and 2, 1, 2. The levels are 1, 2, 3. I have to stay away from this 1, 2, 3. Okay. What we want to show is that for any totally positive matrix, the spectrum is simple and positive. And we know how to show it for Jacobi matrices, which are totally positive. So this is a classical thing, and we actually discussed it on the first day. So I'm going to do something to this network which will preserve all the spectral parameters, all the spectral properties. So we know that multiplication for networks is concatenation. But what is refactorization for networks? So what is a refactorization? So refactorization, let me put it here. If you have two matrices AB, we know that the spectral data for AB and BA will be the same. Well, so what is AB and BA in terms of network? We just cut it somewhere and reglue it on the other side. And I can do it just to the edges. So I can start with this edge. And regluing means that I can put this edge on the other side. So I'm just going to perform this surgery in front of you on the board. And then I'm going to use all the moves that we know how to use without changing the actual matrix. So I can erase this edge over here, okay? It becomes edge over here. By our computation relations, I know that edges that go like this can be moved one about the other, so I can move it over here. Square move, which is essentially refactorization, allows me to move this blue edge over here. So weights are changing, right? And there are these formulas one can write, but we don't have to do this. And then, again, oppositely inclined changes commute. So it goes, oh, sorry. Okay. So, yeah, so, sorry. Let me do it again. So blue edge went over here. Okay, maybe I will just indicate how it moves. So this is step 1. This is step 2. It just moved across this end. Then square move gives me step 3. Then I can move it over here. It gives me step 4. But then two parallel edges with no interference between them can be glued together. So step 5 is that this edge now they become glued together. So we started from here, and it moved, and it ended up over here. So now I can erase all the previous history. Okay, and this is what I obtained. So what happened is that the number of northeast edges was reduced by 1. Okay, and now I can do the same story. Well, the same thing with this guy. So let's do it also. So this guy, so let's just mark it as a step 0. It was here. I can again reglue it on the other side. So step 1. Do refactorization. So for that I have to space my things a little bit differently. So do refactorization. This will be step 2. Move now across this new edge, step 3, and step 4. Is this what I wanted to do? Yeah, maybe. It's over here. Let's erase all the steps that we did. So this is gone. This is gone. This is gone. This is gone. So notice that, well, yes?
What exactly are you calling refactorization?
Refactorization is a square move. Yeah, edges like this becomes edges like this.
On the very first step, when you take the edge from one side,
Sorry. That is, yeah. Refactorization is taking edge from one side to another, and this kind of, this is square move that we talked about. All right, so see that now I have just 2 inclined edges on both sides, and then the next step I'm just going to draw the result, because now we know how to do it. I will take this one again, go on the other side, flip here, refactor, and where will it end up? It will end up over here. And what do I see? I see a tridiagonal matrix. Tridiagonal matrix has, well, positive, totally non-negative tridiagonal matrix has positive distinct spectrum, and that's it. We don't need Perron-Frobenius. I didn't change the spectral data at any point in this picture. All right. So what would be convenient for us actually is instead of refactorization, reimagine this moves from one side to another as some transformations also of a network. So here I can kind of went out of the network and then back into network on the other side. So we can do this by slightly deforming our picture. So let me just draw it like this. So this is my initial network. Doesn't matter what it was actually at this point, but let me keep it now tridiagonal. And instead of planar network, let's just make it. Let's just make this picture into a picture in an annulus, right? And then these movements of edges. So suppose I had this blue edge, the initial movement. I can say, well, it's the same edge. I just redrawn it. This one is the same thing as drawing it over here. Okay. So what we can say about all of this is the following. We have all these kinds of transformations where we have, okay, so let me now be even less specific about what's inside. So we have some network over here, something, doesn't matter what, let's call it network N. Then within this annulus, we do whatever transformation we can to this network. We have a list of what we allowed. And so we've done sequence of elementary transformations. And we obtain now, okay, it will be even more symbolic here, A prime, or network, so N prime. n prime. So this corresponded to matrix A, this corresponded to matrix A prime, and they are similar. Okay? So this way we can design now a discrete map. It is a discrete map. All transformations are discrete, right? So we had something here. We did all these moves. We obtained something here, and it has conserved quantities. Conserved quantities are eigenvalues of A, traces of powers of A, characteristic polynomial, whatever it be. Now, to make it into true dynamical systems, we need, well, several things. We need to coordinatize this picture in a consistent way. So in terms of networks, it means that if I started with something that had certain shape, I better have something of the same shape, but possibly different ways. Because the dynamical system, it should map, so it has a phase space, and it should map phase space into itself. So, so let me now do all of that to describe discrete order equations that we talked about. So what do we do with discrete order equations? So I have, again, it's enough to consider 3-by-3 case. This is my discrete order. I'm not gonna, well, okay, let's complete it to an analysis. Okay, so this is LR in the terminology of a previous talk. So what can I do with it? I can do now by doing this moves around, it becomes RL, right? But in my terminology, it's not yet a discrete map because this picture is not the same. It's still it's tridiagonal, but it's not the same. So what I have to do then square moves. And square moves will give me, my analysis is becoming smaller and smaller, but square moves will give me again the same picture, but with different weights. And we have formulas for all the weights, I don't have to write. And so here to here is my discrete Toda lattice. Okay? So now we can try to design a lot of maps like this, and they necessarily have conserved quantities. But to talk about integrability, we need more. We need the correct number of parameters, and we need a Poisson bracket. And we need to describe it somehow, again, using the same combinatorial picture. So, here we also need to work kind of at cross purposes, because in terms of parameters, well, you need as few as possible. You don't want any redundancy, right? So I can put weights, for example, on all the edges, but that will be too many parameters. And in terms of Poisson bracket, it turned out that it is more convenient to put as many parameters as possible. So I will explain what I mean. So, okay, let's, so coordinates, it is convenient to replace edge weights with what's called face weights. Okay? And I will explain it on again on this 3-by-3 example. But imagine now that this is just front panel of an analyst, right? So now I will add some weights over here. So this is D1, this is D2, D3. Let's say C1 minus, C1 plus, C2 minus, C2 plus. And we know that there is a gauge action here, so I can multiply all incoming arrows by some parameter into a vertex, and then divide all outgoing by the same parameter, and boundary value doesn't change. So what I have to do is design something which is invariant with respect to this gauge transformation. And what is it? So what you can do, you go around the face, this is a planar graph, right? So you can go around the face in, say, clockwise order, and you encounter some weights. And if, so let me draw arrows so that we remember and so if clockwise order is consistent with direction of the arrow, you put corresponding, so this will be our weight W, corresponding parameter, H parameter in the numerator, and if it is not consistent, then in the denominator. So weight sitting in this face is going to be D2 over C1 plus over D1 over C1 minus.
Directions are left to right?
Yes, I always, yeah, for us, I always left to right, okay? And then, so this goes here, and then what goes here and here? Well, in the, well, here and here. In the annulus, it is the same face. So let's call this one U, and here it will be just C1, and then I'm going all the way around, C1 plus, C1 minus. Okay? So, and it doesn't have to be done just for Toda networks, right? You can do it for any planar network, and not just planar, we'll talk about it. So we know how to coordinatize. And notice that now we have exactly, in this case, 2n minus 1 parameter, and I just have to tell you that, and we have n conserved quantities. But one of them, the determinant will be Casimir, so then everything matches. We'll have n minus 1 conserved quantities, 2n minus 2 parameters. That calls for complete integrability if we have also Poisson bracket and involutivity. So now we have to define Poisson bracket. And so for Poisson bracket, we do kind of the opposite. Here we reduce numbers of parameters. But for Poisson bracket, we put weights on all, not just even edges, but on all half edges. Because we want to build Poisson bracket for something very, very simple. So it's time for me to say that what was hidden all the time in these pictures, these vertices actually are different. They have different colors. They're all trivalent vertices, right? And we have vertices of two types. Some have one incoming and two outgoing vertices. Some have two incoming and one outgoing. Okay? So now, so in this picture, it is made out of this little things of the following shape. We have things of this shape, and we have things of this shape, and we can glue everything from those. So now that I put on every half edge, I put a weight, I can say that here I have A, B, C, and here I have A, B, C, okay? And I'm going to define a very silly Poisson bracket. So the only non-trivial brackets will be A, B in both situations. A, B, bracket of A and B, Poisson bracket of A and B is equal A times B. Okay? It's called quadratic multiplicative, log canonical, torics, or there are many names for this Poisson bracket, but this is what I'm going to do. Yes?
I'm a bit lost.
Yeah.
So you replaced the edge weights with face weights, right?
No, that was to write down these coordinates, the minimal number of coordinates.
Okay.
Now I'm trying to do now I'm going to define a Poisson bracket. And for that I need the maximum number of.
So Poisson bracket on what? Sorry.
On matrices, on networks, I will explain what it comes. Okay. So at this point I'm defining Poisson bracket on the space of half edge weights. So
what is half edge? I mean,
so
C1 plus. So C1 plus is the weight
C1 plus now becomes a product of some weight, let's call it alpha, and another weight, call it beta.
Oh, I see.
Yeah, so I'm doubling the number of parameters, which was redundant to begin with, but I will explain why. Okay, but I can define this kind of Poisson bracket. It clearly satisfies Jacobi identity if you assume skew symmetry because.
But it does not assume, it does not satisfy skew symmetry.
So skew symmetry you impose. So you see, I told you the only brackets that you need to know. The only non-zero brackets are A, B here is time A times B, and then BA will be automatically minus B.
Oh, I see.
Yeah, but other than that, if you take logs, this is a constant Poisson bracket.
Yeah.
All right? So it seems silly, but well, what you can, but we know that each network corresponds to a matrix. So if I have a network N, so this is network, I construct from it a matrix A of N, okay? So now this network now has, I don't know, gazillion of parameters, possibly because now I'm not talking about reduced words, just any network at all. But this matrix has only n square parameters, right? So in general, there is no guarantee that if I define this Poisson bracket, it will produce a normal Poisson bracket with, well, just intrinsically defined within A. Okay, so nothing guarantees that, but that's a theorem, right? So this is a theorem. So this is our theorem with Misha and Alec. That so this map, so this well, we can call it boundary measurement. This map that builds a correspondence measurement map. This one induces on A a quadratic Poisson bracket, and it is not just any bracket, it's so-called standard Poisson-Lie bracket on GLN. I will not write the formula now because it will be in the slides. But it is well-known Poisson structure in integrable systems, which in particular guarantees that all spectral invariants are always in involution. Okay? So that's the story. We have some combinatorial manipulations with conserved quantities. And because we can define such a Poisson structure, also combinatorial, they match nicely. So, yes?
How do you divide each edge weight into arbitrarily? Any way works to get?
Yeah, anyway. Okay. Yeah. So that's the magic of it. You can just, and you can build arbitrary networks. You can make them wider, and but this is also always true. Okay. No. Now we don't, because now our edge weights are variables. Well, yeah. Okay. But if you start with them positive, all transformations are positive, so it will be positive. Okay, but again, this is a good comment because positivity somehow was connected with planar graphs, but now no one prevents us from extending this. And so let me now go in parallel and just extend this everything. So we just talked about networks in an annulus. Well, another way to look at an annulus is a cylinder. So again, I'm drawing the same picture, so it will be the same picture today. 1, 2, 3, 4. But now I imagine that this is just one side, just front of a cylinder. Okay? And so I can draw networks like this also on a cylinder. So I can imagine that there is another edge now. So there is 2, 1, 3, 2, but suppose there is another edge on the back of the cylinder that comes all the way to 3. So this is an edge, and I can put a weight on it as well. Okay? And similarly, I can have an edge that goes on the other side of the cylinder and ends up here. Okay? Okay, so I can define my phase coordinates, it's still a surface in the same way. I can define my silly Poisson bracket. in the same way. But this result does not survive as stated. We need something extra. And what do we need extra? Well, we need, because now we have a cylinder, we have to count how many times these edges may possibly go around the cylinder. So to do this, we introduce what we call the cut. So it will be another structure. So suppose it's on the other side of the cylinder. So it will be in green. Okay? And then it's also directed. And then every time my edge crosses this cut, I multiply the corresponding weight to something else, to what will be also called spectral parameter. And if it crosses the cut in a positive way, it will be spectral parameter lambda. And if it crosses in a negative way, it will be lambda inverse. And in this way, now we define our boundary measurement is exactly the same way. The matrix is defined, so it's now, call it M. It now will depend on lambda, okay? But it will be, again, now sum over all paths from I to J of product of weights along the path times lambda, well, roughly speaking, raised into the power of intersection index of our green cat with the path. So, all right, so here, or you can just say that this modified, you use in the product modified way. So one can prove that even if there are cycles and everything, this is still a rational function, okay? Right, so what happens with this part of the story? So boundary measurement induced on A of lambda now induces a quadratic Poisson bracket, but now it's bracket for matrix polynomials, and this is called, again, formulas later, trigonometric R matrix Poisson bracket. So again, the very famous object in integrable systems, and in particular, now we know that all, this is corollary, all coefficients of the determinant of M of lambda minus Z identity, so a lot more coefficients. All these coefficients are in involution. They all Poisson can. Okay? All right, so I'm almost ready to go to slides, but now what does this Poisson bracket do for our phase coordinates? We need to match these things together. So again, I'm going to come back to one of my pictures, and then...
Sorry, when you say coefficients, you mean as coefficients in the bivariate polynomial?
Yeah, bivariate polynomial, yeah. All right, so one more time, I'm going to redraw the same picture. I'm sorry about that, but we need it. So 1, again, 2, 3. So we have an annulus, back to annulus. I just want to give an example. And then we have this network. And here I want to emphasize which vertices are filled in and which are not. Okay? So phase coordinates, they sit over here, right? In phases. So in this particular picture, there are 4 of them. Okay? I want to compute Poisson bracket between phase coordinates. I know this, so this is a statement that Poisson bracket between any 2 of them will be their product times an integer. So if it's an integer, of course it's signed because of skew symmetry, I can show these integers as certain number of arrows coming from one to another. How to compute this number of arrows? So the rule is the following. if two faces are separated by bicolored edge, then I draw an arrow in such a way that the empty vertex is on the left. So let me start. So I have an arrow from here. Yeah, it's a good point. From here to here, okay? What else, other arrows I have? I have arrow from here to here. But in fact, here it's a double arrow because this face is like that. So there will be two arrows here, and there will be two arrows here, and there will be one arrow here, and then there will be two arrows here. And so what we have is what's called a quiver. And it's not just quiver, it's a particular case of a quiver for Q systems that we have two experts on sitting right here. Okay? So what it boils down now, phase coordinates are some variables that we're going to investigate, and Poisson bracket is just given by a quiver. And this brings us to cluster algebras. Finally, right? And so now, in the remaining half an hour, I'll switch to the computer because I need more complicated pictures and formulas, and then we consider some examples.
Ask me to remind you to share screen.
Okay, yeah, I will share screen first. Yeah. Okay. If it will listen to me. Oh, sure. Yeah. It's all, yeah, sure. Okay. All right. So, so this is a title for the remainder of the lecture, and I should point probably here. Right? Oh, yeah. Keep forgetting. Okay. Let's see. Yeah. Okay, so now I'll have to define, so there is no escaping now. Philippe didn't want to define it yesterday. So I am going to give a definition of a cluster algebra. It's long, but now we have examples, okay? So what is a cluster algebra? Cluster algebras defined by Fomin and Zelevinsky, and well, they became a ubiquitous tool in many fields. So they grow from seeds. And seeds are made of two components. It's a set of variables, and then so-called exchange matrix. But instead of exchange matrix, we're going just to deal with Q-symmetric case, and we'll just say that B is an adjacency matrix of a quiver. So adjacency matrix is just signed number of arrows, between edge, and okay. And so what we can do with these seeds, we can mutate them. So in certain direction, we pick a variable, and we're going to change this variable. So we will replace it with something else, and the something else is given by this very simple, formula. In terms of quiver, I'm going to define it. So let's think about it. We know such formulas from linear algebra. So old variable times new variable is the sum of two monomials. Sum of two monomials, all the product of all the variables that point into the selected one, and plus sum of all the variables to which the selected one points. Think of the Inoue-Jacobi, Short-Plücke relation, Ptolemy, all of them can be written in this way. Okay, and this is actually what's happening here. All right. We have another set of variables called so this is Y mutation. So what you do again, so what do I do here? So my variables X attached to vertices of in a quiver. So I can go around the vertex. I'll show example. Yes?
Is the second Y in the formula?
Yeah?
I think the second Y is not here.
Yeah, it's not here. Right. It's thank you. It's a typo. Yeah. So you go around the vertex, and you put variables that are adjacent to this vertex in the power equal to the signed number of arrows. So it's a monomial. And they mutate in the following way. So there is a part which is just defined by just my quiver, But depending on the sign, I also have yk raised into this power. Bki plus is, if it's positive number, it's the number itself. If it's negative, then it's 0. Okay, well, some bilinear transfer, birational, sorry, transformation. That's a definition that follows, well, not definition, it follows from the previous. All right, so, well, but then, unfortunately, you have to mutate matrix B2. I will flash it because, well, the formula, don't look at it. No one does that. People usually look at mutations of quivers. There are rules for mutations of quivers. Again, we don't have much time to study them, so I will illustrate them on examples. All right, but rules, there are 3 rules, right? Combinatorial. So what do you do? So here is a quiver. I want to mutate this quiver at vertex 2. First of all, what I do, I find all directed 2 paths going through 2. And I build a shortcut. Shortcut 1, shortcut 2. Then I reverse direction of all the arrows which are incident to the ones that I selected. I reverse them all. Well, in this first mutation, this is all I can do. But there is a third one, because what I didn't tell you, but what is obvious from the pictures, my quivers are not allowed to contain loops and 2 cycles, directed 2 cycles. So let's mutate at 4. Again, I build a shortcut. Shortcut would go from 5 to 1. It cancels. Yeah, so that's the third one. So you have these mutations, you can get some nice pictures. In this case, you will only get nice pictures. More often you just get crazy pictures with thousands of arrows. But when you study integrability, you don't want to mutate just willy-nilly. You have to find a nice order of mutation. But so this is an example. In fact, this is not just silly example. It actually illustrates a cluster structure of Grassmannian GR 3-5, I think. Anyways, all right. So those are the rules. And then immediately we will introduce Poisson bracket on cluster algebras. Again, in a very simple way. So we call it log canonical Poisson bracket because we have these variables and we will require, so then we mutate them one by one. We can repeat these mutations 1,000 times. And again, we get a tuple of variables, say x1 tilde, xn tilde. And we require that after all these mutations, in every single cluster, the Poisson bracket between any 2 variables is a Yeah, it's not my computer. But I don't know what happened to Zoom, but I can open probably the slide.
It's open.
Oh. Oh, right. Okay. What? Okay, thank you. Yeah, so so it has a simple structure, right? And it's called log canonical. But we require that this happens at every single cluster. After all mutations, this is preserved. And then we call such Poisson bracket compatible. Okay? All right. So we have the theorem that if my adjacent symmetric quiver was of full rank, then such a bracket exists. Okay? And instead of writing what these omegas are, we can write it very nicely in terms of y coordinates, just as we saw over there on the blackboard. So in terms of y coordinates, Poisson bracket is the quiver. So for y coordinates, the Poisson bracket between them is a signed number of arrows between them. Okay? So what it tells me is that if I mutate, and suddenly got to the same quiver, then I get the same Poisson structure, so it's a Poisson map. Okay. So what are applications of this construction? So Alec, Misha, and I, for a long time, we're using it to construct cluster structures in coordinate rings of Poisson varieties. Meaning that you have some well-respected Poisson varieties, a group, Lie group. You pick a Poisson bracket, then you try to find one coordinate system which has this log canonical property, and from that you can build a cluster algebra. Okay, so Grassmannians, Poisson Lie groups, so there are many examples. But for us today, it's more important to look at Y side, it's Y transformations. And they were using construction of cluster structure in Teichmüller spaces, and then in this great work of Fogg-Goncharov in high Teichmüller space. And there are connections also observed by Fogg and Goncharov with dialog functions, and then polylog as well. And that is that you can actually interpret Y mutation as a Hamiltonian flow, or one time of Hamiltonian flow of a Hamiltonian given by dialog function. It's very simple. So this Y mutation is Hamiltonian flow plus canonical change of variables, which is nice. And so what can you get from that? First of all, you can get their logarithm identities. So suppose I have a periodic sequence of mutations, meaning I mutate, and I obtain the same quiver with the same variables attached to it. It can happen. Whenever it happens, you have a nice dilogarithm identity, and this includes the Zamolodchikov, it's conjectured from Zamolodchikov conjecture and the vast generalizations. Yes?
And X and YK are interchanged. Integral is over X.
No. So here's variable is YK. Just X here is just to where we integrate.
But if this is D2 of minus YK, YK is.
Oh yeah, here. Yeah. Sorry. Yeah, you're right. Yeah. Sorry. Yeah. You're right. So one can have typos even. There's a slide. Okay, but then. Second application, this is relevant to us, is that cluster integral maps then arise from mutation periodic sequences of transformation. So again, what does that mean? So I mutate, and I obtain the same quiver, but different functions are now attached to this. Not the same as that I started with. They are by nature, they are rational functions of initial variables. So I have a birational map that automatically preserves the Poisson structure. It does not ensure integrability yet, but it already preserves Poisson structure. And so, I want just to go through two setups. One of it, again, will be about Toda and around Toda and generalized Toda, and another one, and it corresponds to planar situation. And another one is pentagram map, which became this prototypical map to study a cluster integrable system, and this lives on a torus. Okay, so I have these two stories, and one is Coxeter Toda flows on GLA. So let's just start with Toda flows. Here I just wrote equation. So X is an n by n matrix. This is a so-called Lux equation. I just wrote it explicitly. dx by dt is commutator of X with the following gadget. You start, we take power of xk, and then you project it to strictly upper triangular part, and then subtract projection to strictly lower triangular. You get a very nonlinear equation, and it is integral. So not just equation, hierarchy, because there is k here. So they state, so what is the Poisson bracket here? This is the one that I referred to on the blackboard without explaining. This is standard Sklenin bracket or standard Poisson-Lie bracket. Again, there is a formula. This formula involves this operation of this kind of skew projection. It's called standard R matrix. It's a statement that this is indeed a Poisson bracket. Moreover, why is it Poisson-Lie? It respects multiplication. So multiplication map is Poisson with respect to this bracket. So it's well studied from the 80s in the work of Drinfeld, Semenov, Tenshansky, and so on. So we have a Hamiltonian flow. Now, there's a huge Hamiltonian flow, but you can restrict it to smaller subsets of GLA. What are these subsets? They're so-called double Brouwer cells. In double Brouwer cells, well, I define like this. You take two Brouwer decompositions with respect to upper triangular and lower triangular matrices, intersect them. This is double Brouwer cell. Coxeter double Brouwer cell appear. I don't know why my lighter stopped working, but they appear when this permutation U and V are Coxeter elements. So they're just products of n-1 distinct elementary reflections, as we saw in our pictures, like S1, S2, S3. or S3, S1, S2. They all, well, this is the same thing, but S2, S1, S3, and so on. All right. So the claim is how it's related to Toda. All these manifolds are invariant with respect to our Poisson bracket, so flow restricts to them. And for Coxeter U and V, Toda flows actually restrict to a completely integrable system. Well, in fact, they're always completely integrable. But here it's kind of obviously completely integral because we only need spectral data to ensure complete integrability. Why? Because of dimensions. Coxeter element has n-1 things in it, right? So we have n-1 plus n-1 plus n. That seems to be 3n-2. Determinant is a Casimir, we forget about it. And then, and then we factor by the conjugation by a torus. And that kills n-1, and so we have 2n-2 and n-1 independent integrals. All right, and discrete Toda flow is part of this, is a time-one map of a member of this hierarchy. And we'll already see many times how it's done. It's refactorization. So what is included in this setup? Usual Toda lattice, if U and V are selected like this. Relativistic Toda lattice, if U and V are equal, that we saw in previous talk. CMV matrices, so we have so-called bipartite Coxeter words. This is Ablovitz-Ladik lattice, Picon lattice, if you just listen. So many. All right. So here's an example, again, another of network parameterization, what it is, what the corresponding matrix is, using boundary measurements. So this is, you can check. So how do you solve them actually, all the system, how you can solve them? You solve them using so-called Moser map. So you take your operator X, and you consider its resolvent, and you take one matrix entry of the resolvent. It's necessarily a rational function. You can expand it using Laurent expansion. In the denominators, you have moments that we heard about, okay? And they evolve linearly when X itself evolves nonlinear. So this linearizes any Coxeter Toda flow. And you can describe solutions, everything in terms of Hankel determinants. So now we can not concentrate on formulas, but there are formulas, again, similar to what we saw in Sujimoto-san's talk. And instead of epsilon, I used eta. So his epsilons, well, sums of his epsilons are my etas here, right? All right. Oh. All right, and you can restore all the parameters using these nice determinantal formulas. Don't look at the indices. All you have to notice that these are nice expressions in terms of Hankel determinants. Okay, those are epsilons here. All right, so that's a formula. But this is not what we're talking about. We're talking about network. So yeah. So now all the systems are very similar to each other because they're linearized by the same kind of construction. So they're related by what's called Backlund, I missed the umlaut, Darboux transformations. And in particular, again, to relate to the previous talk, we have explicit formula of how to relate Toda to relativistic Toda. So there are, again, some scary looking formulas, but if you're used to them, they're not so scary, but they explicit birational formula that tells you that if you have a Jacobi matrix and it evolves with respect to Toda equation, out of it you build such expressions, and they will be parameters of factorization for relativistic Toda, and it will evolve as a relativistic Toda evolves. All right? So they're all related by Backlund-Darboux transformations. Okay. So again, we saw this, but now I want to use this network parameterization to replace all the scary formulas by pictures. So what is a Moser map? Here's my Moser map. So we're talking about computing a matrix entry of the resolvent, right? So now I'm in the annulus, and I have this cut that we talked about. So anytime I cross the cut, my weight of a path is multiplied by lambda inverse. So and of course here I can, again, I don't know why pointer doesn't work it, but I can point with finger as well. I can go around as many times as I want to, right? So this lambda tells me how many times I rolled around before going out. And if you think about it, you'll get exactly what? I will get out, turn around, say, in any possible ways 3 times. What will it give me in terms of this picture? In terms of this picture, it will be exactly 1 entry of the cube of the matrix represented by this. What we were talking about when we were trying to draw pictures for Hankel matrices. So this is my Moser map. So now in the setup I already talked about earlier, we have some transformations in the annulus which preserve, spectral invariance, and B, can bring one of these systems of equations into another system of equation. And if we're doing this transformation and end up with the same shape of the picture, then it becomes a discrete integrable map. So it's together Backlund-Darboux transformation and integrable. Okay, and then what are the quivers? Where are the cluster algebra? Cluster algebra is right here. So in my network, I had this white and black vertices. I put coordinates in faces, and I draw a quiver. So quiver is drawn here with this red dots, according to the rules that I previously described. If 2 faces are separated by bicolored edge, I put an arrow in such a way, well, in completely opposite way to what I described, but it doesn't matter. So that white vertex is on the left. Well, there it was on the left, but then I can claim that on the board that white vertex was actually green. So yeah, it is consistent. Yes?
What happens when you have a monocolored edge?
A monocolored edge, then there is no error. Because you can contract it and do things with it. Okay. All right, so we have a quiver. Cluster variables are these Hankel determinants out of which I made my solutions. And cluster transformations are modeled on determinantal identities. And Backlund-Darboux transformations are compositions of these elementary network transformations. So I'll just show a picture. So again, it's just illustrative. So I took here, what did I take? C2 plus on one side, put it on the other side, well, exchange monocolored edges, do all the transformations that I'm allowed to do. Okay, and this is all. All right, so sorry about Russian, but yeah, that's the nature of things. Okay, so that's one example. Another example is a pentagram map of Reed-Schwartz. So what is a pentagram map? So he was discovered, or it was discovered by Schwartz in '92, and Rich quickly realized that it must be integrable because he wrote programs and he saw that this integrable type quasi-periodic behavior. So what is a map? You have a polygon in a projective space. So it's a projective class of polygons, and you draw short diagonals, and they intersect, and they give you another polygon. And that's a map. That's called a pentagram map, and it acts on projective equivalence classes of closed n-gons. So for pentagons, actually, it is an identity. It's a good exercise in projective geometry, but in n equals 6 is involution, but then it's a map. All right? Or you can extend it to so-called twisted n-gon. So what is a twisted n-gon? So what is polygon? It's a sequence of points which is closed, right? Twisted polygon is sequence of points, but the first one is related to n plus first one by a fixed monodromy, fixed linear transformation, and then second to the n plus second with the same monodromy, and so on. If this monodromy is 1, we get a polygon. If not, it's twisted. All right. So this is a map, and this is integrable. How do we show that something is integral? We need coordinates, we need Poisson bracket, we need conserved quantities. Okay, here are coordinates. So this is piece of my polygon. I consider 5 consecutive vertices. I draw lines through them until they intersect. It gives me 2 lines. Each contains 4 points. 4 points on a line gives me a cross ratio. Cross ratio is a projective equivalent. So each corner gives me 2 coordinates x and y. And this is how pentagram map acts. You can compute it. It's, again, nice birational transformation. So Ovsienko, Schwarz, and Tabachnikov much later showed that this pentagram map preserves a Poisson bracket which looks suspiciously similar to what we talked about cluster Poisson bracket. And it is completely integrable in space of twisted n-gons. All right, and its continuous limit actually is a Boussinesq equation, which is also very nice. So one of these integrable equations of water wave in the theory. Okay, and so in the closed polygons, it's more complicated to show that it's completely integrable. This was proven by Solovyov and separately by Ovsienko, Schwarz, Tabachnikov. And then there was a lot of work on generalizations, interpretations of this pentagram map. This work is still continuous. Some of the people present participated in this work, but we just want to talk about cluster interpretation of this. And this was initially obtained by Max Glick, student on Sergei Fomin, who realized that if you draw this quiver, so it's bipartite quiver. If you draw this quiver and do this Y cluster transformations, first at all the purple vertices and then at all the yellow vertices, then the quiver will become, well, actually opposite of itself, but you can say up to change in inner and outer, it becomes the same quiver. And corresponding birational map is equivalent to pentagram map. So there is a change of variables. X and Y change to something. Okay, so what is nice about this quiver? This quiver can be drawn, you cannot see it maybe right away, but think about it closely. It is not planar, obviously, but it can be drawn on a torus. So you can just imagine this inflatable torus that kids swim with in a pool, right? So, and you can see that if you put kind of half of these arrows will be on the front of this inflatable tube and half will be below. So it's on a torus. This will be important. Oh, sorry. Yeah, okay. So, as I said, pentagram map is a sequence of mutations of Y variables attached to this torus. Quiver is preserved means that we have invariant Poisson bracket. Now we need conserved quantities. So, well, first of all, we have a quiver on a torus, so we can reverse all the procedure. So we saw in previous situation, we had a network, bicolored network. We've drawn a quiver dual to this network. Now we do the opposite. We will draw a network which is due to which this quiver was due. So it becomes a network on a torus. It's still so this white and black vertex is still on a torus. So we need a boundary measurement. Well, how did we get boundary measurement from the annulus? We cut it, we obtained something planar. Well, you cut the torus, you get a cylinder. You get a cylinder, as I explained, you get boundary measurement rational matrix. So what are our cluster mutations? They can be described again by the same network transformations, and what they amount to so-called Moser-Veselov map, which is again refactorization. Boundary measurement can be factored as M1, M2, and then we switch order. And that's my pentagram map. What does it tell me? It tells me that all the spectral invariants are preserved. And then you have to show that they're independent and there is enough of them. But so that's, and so what are we missing? We miss Poisson bracket. But I already told you what it is. So again, no time to unpack this formula, which used to be called Leningrad formula, now called St. Petersburg formula, I guess. But anyways, there is a Poisson bracket. So Sealy bracket on networks induces trigonometric R matrix Poisson bracket. So I will say a word or two what it actually means. So this side just tells you, so if I have to write Poisson bracket between two rational matrix function, I need to write Poisson bracket between every entry with any values of lambda and mu. So this just says we have a table of all possible Poisson brackets. And it has size n squared times n squared. This is the size, this is what where tensor products live. So this is the formula, actually, what to put in each entry. And then you have to show that this is Poisson-Lie, that this is Jacobi. Yeah, and R is this is solution to the classical Young-Baxter equation.
What happens if lambda equal to mu?
Well, yeah, because it will not make sense because you have some cancellations actually, but you shouldn't write lambda equals to mu because lambda and mu for matrix entries is 0. So yeah. Yeah. Well, it's not a problem. It has a pole. It's it's allowed to have a pole. Yeah. Yeah. So this is called trigonometric arguments. Yeah. Okay. So this is all we need for complete integrability of pentagram map. But in fact, this is a very general picture. So spectral invariants are in involution because this has been proved long time ago in the theory of integrable system, going back again to Semyonov-Tenchansky and Rayman and so on. Okay, but this is a part, so let me just illustrate this. So this is a dual network for the quivers that I've drawn before. So you perform the square moves in all the squares, okay? So moves are like that, we discuss them. You'll get something which looks different. It looks different, it represents the same boundary measurement matrix, so this is not what we want. So instead, what we'll do, refactorization. So I represented cylinder as an annulus. I cut it in the middle, right? And then inner part, I stretch it, and I glue it on the other side. And I claim that as a result, I'll get the same kind of picture, but with different weights. That's our map. All right? So most general, what's going on here? So this is our theorem with Misha, Sergey, and Alex that, so you start with a toric quiver drawn on a torus. You draw a network, dual to the quiver. This network doesn't have orientation yet. You can cut the torus and reorient this network in such a way that everything flows again from left to the right. Then it gives rise to a boundary measurement matrix that depends on only on the cluster variables. And then spectral invariants of this matrix form an involutive family of functions with respect to this cluster Poisson structure. All right. So now I'm out of time, and I only have two slides, and one of this is more a joke. So, and another one is there because Philippe mentioned yesterday this general construction of Goncharov-Kanian of integrable systems from dimer configurations. Okay. So, and this slide is called "Let's Just All Be Friends," and because thanks to Anton Izosimov, we know that these two constructions are exactly the same. So if you have, don't read this. So what it says is the following: if you consider our construction, then there is a dimer configuration for which you can build an integrable system, and it will be the same or equivalent integrable system, and vice versa. All right, and more about that. So this is partly joke, partly shameless advertisement. More about that is written in our review with Anton in Encyclopedia of Mathematical Physics, but I want you to pay close attention to the header. So for some reason, before it went to print, it appeared online on Springer website and the reference module on material science and materials engineering, which proves that what we're doing is really applied science. So I'm going to end with that. Thank you.
For virtual lectures. So is there any question, please?
So when you have a quiver, you can mutate it and perhaps you come back to the same quiver, and then it could be integrable.
Yeah.
But perhaps there's also another direction of mutations that take you back to the same quiver. Is it always integrable? If in one direction it's integrable, in the other, in every other direction it is also integrable?
It's it's a good question. My guess is that it will be, but also this integrability usually for all examples that we know only happens with quivers which are embedded in a torus, and so maybe that's
Well, for the bipartite graphs, it's always the case, but when you get out of
yeah, no, I think it's true, but yeah, I actually haven't shared this. This is a good. So for that, you just need you need to study cluster modular group and see. But I believe it is true. Yeah.
Thanks.
I missed the connection between the M and the A. Can you just?
Oh, sorry. Yeah, the connection is the usual one. I forgot to change the notation. Thank you.
I have a very basic question. At the beginning of slides, you said that there is a, oh, maybe I didn't understand. There is a like a Poisson bracket on X variables.
Yes.
I know that there is a Poisson bracket on Y variables.
Yeah. So it was also on the slide. So So to Poisson bracket on the X variable is the constant of this Poisson bracket, right? Because it has the structure constants omega ij. So the matrix of these coefficients is essentially an inverse of the adjacency graph of the quiver. So they are equivalent, especially when what's called x to y, x to a map, whatever, is invertible. So it is the same Poisson bracket in a different set of coordinates, because my y variables were made out of x variables.
Mm-hmm. Okay. Thanks.
Yeah. Okay.
So you showed this network correspondence to totally positive matrices, but if I'm interested in lesser things like just positive entries or 2 by 2 minus positive, is there any correspondence with networks?
So first of all, any matrix at all can be represented by a network, but probably with many extra edges. For example, just to permute two indices, you need three factors. So they can be represented with planar network, but necessarily, well, if it's not totally positive, some of the weights may be negative. So I actually don't know how to describe networks to just preserve TP2, what's called. So yeah, it's a good question, but there should be some relations between weights or number of parameters. Yeah, that could be the case. Thank you.
Is there any other questions or comments?
Is there a higher genus story?
So it appears that all the examples are on a torus. So I've seen some talks about the Hitchens system in this context, where genus could be arbitrary, but with quivers which are not on a torus, I haven't. Well, another problem with that is that it's not so easy to write boundary measurement metrics. For one thing, so why did we have just one cut here? Because we wanted to make things planar, so you will have multivariable polynomials, and yeah, that could be a complication. But yeah, I don't know I mean, not integrable. Networks you can write anywhere. Poisson bracket you can write combinatorial one anywhere. What it amounts to, it's not exactly clear. Yeah. Maybe, yeah.
All the systems you showed were A-type, right?
Yes, they were A-type. So, so there is, of course, network representation for other types. Sometimes it's planar, sometimes it's not. So there is work of Simon, your student, and then recently Anton Zosimov had a paper of how to introduce symmetries in A-type networks to get B and D-type, or B, yeah. So you can, and I think G2 you can do. It's planar, but. Well, yes, that's an excellent question. And yeah, you can quantize, and moreover, you can make the things fully non-commutative. So there is this work of, in particular, so it started with Mary Beth, but there is a work of Artamonov, Ovenhouse, and Shapiro. And how you quantize, so, well, first of all, you replace my advisor taught me how to make things non-commutative. Replace small letters with capital letters and things no longer commutative. But yes, no, I'm talking about fully non-commutative. But yeah, but there are quantum versions of this as well. Yeah. Yeah, but yeah, I think that it's important that you can even make it completely non-commutative. Completely non-commutative. Not Q-commutative, but completely non-commutative. But then there is a problem with Poisson brackets, and they have to be replaced with double brackets, double quasi-Poisson brackets, and such things.
Is there any other questions or comments? Okay, so thank you, Misha.
Thank you.